In this video, we'll look at a way to measure the strength of fit of a linear model and to explore the impact of what are called leverage points. In previous videos, we were looking at the relationship between the percent of the population with access to clean cooking fuel and the percent of deaths caused by indoor air pollution. We noticed the linear relationship between the two variables and computed the correlation of negative 0.934, which suggested a strong negative linear relationship. And we created models for the relationship between the two variables. First, we made a model to predict the y values given the x values. If we added this regression line to the graph, it would look like this. We then noticed that our model wasn't predicting the y values perfectly, so we made a model that incorporated this error. And now, something we're interested in is how well does this model predict the data? To do this, we'll compute the percent of variation in the outcome variable that is explained by the model. Suppose for a moment that there was no variation from country to country in the percent of deaths caused by indoor air pollution. So all of the country's percentages would be equal to the overall mean percentage of deaths caused by indoor air pollution, which we write as y bar. But of course, there is plenty of variation. Countries with different percentages of the population with access to clean cooking fuel have different percentages of deaths caused by indoor air pollution. And sometimes, countries that have the same percentage of the population with access to clean cooking fuel have different percentages of deaths caused by indoor air pollution. To compute the percent of variation explained by the model, we'll start by measuring the total amount of variation from the overall mean. We'll start by taking the first data point in our list and finding its distance or deviation from the mean. We can represent this amount as y sub 1 minus y bar. And if y sub 1 happened to be less than y bar, then this would be negative. But we're just interested in the overall size, so we'll square it to make it positive. Then we'll repeat the process of squaring the deviations for each of the data points and add their values together. And this sum is called the total sum of squares, or SST. Now, some of these deviations from the overall mean can be explained by our model. That is, our model predicts that some countries will have higher or lower percentages in the mean. Let's add our model to the scatter plot. We label the predictions made by the model as y hat. So let's think about how much of the variation can't be explained by our model. So we'll try to measure the total amount of variation from y hat. Now, if we look at the first data point in our list, out of the total distance from the mean to the data point, our model can explain the first part of that distance from the mean. That is, the model predicted that this country would have a higher than average percentage, but its prediction was a bit low. So the part of the deviation that our model can't explain is this distance from the predicted value to that data point, which we can represent as y sub 1 minus y hat. And as before, we'll square it to make it positive. Then we can look at the distance from the predicted values to the corresponding data points. We'll square each of these deviations and add their values together. And this sum is called the sum of squared errors, or SSE. Now, our goal was to describe how well our model predicts the data, and we're going to measure this using the percent of variation that is explained by the model. To compute this, we'll take the amount of variation from our model and divide by the total amount of variation. This will give us the percent of variation that can't be explained by our model. So to get the percent of variation that can be explained by the model, we'll subtract this quantity from 1. This is called the coefficient of determination, and it is represented as r squared. So it turns out it can be computed by squaring the correlation. In our scenario, the correlation was equal to negative 0.934, so the coefficient of determination is equal to 0.872. This means that 87.2% of the variation in percent deaths caused by indoor air pollution can be explained by the percent of the population with access to clean cooking fuel. Let's take a look at another example. Let's consider the percent of the population living below the poverty line as a predictor for the percent of deaths caused by indoor air pollution. In a previous video, we noticed that there was a positive linear relationship between the variables, and computed the correlation to be 0.661. So if we make a model to predict the values of the outcome variable, we can compute r squared by squaring the correlation. This means 43.7% of the variation in percent deaths caused by indoor air pollution can be explained by the percent of the population living below the poverty line. Now, there is something we need to be careful about here. If we look back at the formula we used to compute the correlation, part of that formula involved the distance that each point was from the mean of all of the x values. In our data, the mean x value is roughly 23%. So if we have a data point like this one, then it has a much larger impact on r and r squared than the other points. This point is called a leverage point. If a leverage point lies close to the regression line, then it increases the value of r squared. And a leverage point will tend to pull the line toward it. For example, if we were to eliminate this point from our data, then the slope of the regression line would change noticeably, and the correlation and coefficient of determination would both decrease in value. Now, it might be tempting to remove leverage points, such as outliers, from your dataset. In general, if outliers represent authentic data, then they shouldn't be removed from the dataset. But it is worthwhile to remember and, if warranted, disclose the large effect that they might have on the regression line and the coefficient of determination. Now, let's review what we saw in this video. In this video, we started with a model for data and asked how well the model predicted the values in the data. To do this, we computed the percent of variation in the outcome variable that is explained by the model. To perform this computation, we first computed the total sum of squares, which was the total amount of variation in the data from the overall mean of the outcome variable. Then we computed the sum of squares of errors, which was the total amount of variation in the data from the predicted values. Then we computed the coefficient of determination, represented by r squared, which was 1 minus the percent of the total variation that is not explained by the model. We looked at two examples, and in one of them we found a leverage point, where its x value was much larger than the overall mean x value, and this would also be the case if the x value were much smaller than the mean. It's important to be on the lookout for leverage points because if they are close to the regression line, they increase the value of r squared and they affect the slope of the regression line.